Hey, honey, don't walk out. I'm too drunk to follow. You know you won't feel this way tomorrow. Well, I'm a little rough around the edges and inside a little hollow. And I'm faced with something sometimes that are so hard to swallow. Hey, but I was born a rebel down in Beauty on a Tuesday morning. Of 1 foot in the grave, 1 foot's on the pedal. I was born a rebel. I was born a rebel. She picked me up in the morning and she paid on my ticket, and screamed in the car and let me out in the thicket. Well, I never would have dreamed that her heart was so wicked. I keep coming back, 'cause it's so hard to kick it. Hey, 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 and I was born a rebel down in Dixie on a Sunday morning. Of 1 foot in the grave, 1 foot's on the pedal. I was born a rebel. I was born a rebel. Even before my father's father, well, they called us all rebels. They burned out our crops and they leveled our town. Well, I still feel the eye of those red-coated devils, and I'm walking around tonight through the concrete and metal. Hey, 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 'cause I was born a rebel up in Beauty on a Tuesday morning. I've 1 foot in the grave, I've 1 foot on the pedal. I was born a rebel. I was born a rebel. Hey, 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 I was born a rebel. I was born a rebel. I was born a rebel.
Okay, good afternoon, everybody. Good morning, good evening, depending on where you're
Hey, honey, don't walk out.
again.
Too drunk.
Uncle, having an uncle.
I don't know what's happening.
Oh, yeah. Encore performance.
Encore, yeah. Seems to have a bit of an echo, so I'm going to have to watch that tonight. I'll mute myself as soon as I finish talking. But yeah, welcome everybody. And you're used to technical problems with us. You know how it works. We've got next episode for you this afternoon, Man from CERN. So Savannah's going to, as we usually do, Savannah's going to give you his part of the episode. He's going to tell you what he has for you today, which I believe today's subject is antimatter. So we're going to let him do that. We're going to hear what he's got to say, and then we'll move on to questions. And we've got somebody on live who's going to ask a few questions, and we'll see how it goes from there. So I don't want to keep you listening to me. So I'll hand you over to Savannah, and we'll get going.
Hi, everybody. Nice meeting you again.
So thank you, Alex, for the introduction. And I would like to start right away. First, just two little things. One, I have noticed that a lot of people are trying, since I started replying on the Facebook messages to the comments with my new profile, the man from CERN. Now, the thing is, when you ask for my friendship, please specify that you are from this group. Say I'm from Las Jacobites, because I'm having tons of messages from pretty girls in bikinis, and it's hard to tell who's real and who's not. So, before I accept this
probably not our listeners. They are probably not our listeners.
So sexy enough.
They're probably not.
Well, that's Facebook. That's Facebook for you. So basically, I will be glad to accept the friendships of all the members of this group, but please say that you are from this group when you ask for my friendship, or otherwise I can't tell. So the second thing is the usual disclaimer, and is that yes, I am the man from CERN. I worked 35 years at CERN, and I left 11 years ago, as creative director. But I am no longer working for CERN, so whatever I'm going to say is my own thoughts and my own knowledge, and it does not involve CERN in any way, although I will talk about the research we do at CERN. Like I said, today we're going to start talking about antimatter, which is a very intriguing subject, and it's one of the big mysteries that they are rather, since I left, they are still exploring at CERN and in many universities around the world. So I guess we can, I see Professor Doom have appeared. I guess, yes, you will be asking questions on the subject. So the way this goes, I first talk for about 20-25 minutes about the subject with the presentation. And then we will have a discussion. So the only thing I like to ask everybody, you and the people who ask questions via comments, is to kind of stay on subject. Anything else that has to do like with quantum theory or parallel dimensions or whatever else, let's leave it for a future session, because every time I receive a question on something which is not on subject, of course I have to introduce the subject, which takes a long time. Therefore, I will talk about all these things in the future weeks to come. So let's try to stay on the subject of antimatter today. So we can proceed. If Alex, you can send the presentation.
Yep, whenever you're ready.
Okay, here we go. So antimatter. This is part of a presentation called Wonders of the Universe that I have been around in private clubs and in schools and university. So the subject of today is antimatter. Last time we spoke about dark matter, and this time we go on antimatter, which is probably the number 2 mystery that we are exploring at CERN. Now I am okay. Send me the first slide. Before asking what is antimatter, I'm going to ask the question, what is matter? We can only talk about anti-something before we know what that something is. So matter is composed of atoms. Matter is everything that you can see or feel or touch. It's all, except for things that you cannot touch, like light. Light is not matter, light is a radiation. So it's energy. So we have 2 forms of things in our universe, matter and energy. So matter is whatever consists of atoms. And we see matter basically as everything that surrounds us, from the stars to ourselves to animals, plants, this table, this computer, it's all matter. Is made of atoms, which in turn are made of particles. As we look at this picture, we certainly remember from school that an atom, according to the Niels Bohr definition, the Bohr-Rutherford definition, it has a nucleus at the center. This nucleus is made of protons and neutrons. In turn, protons and neutrons are made of quarks. And there are typically 3 quarks in a standard atom, in a standard proton or nucleus in a standard atom. And this quark can be up or down. So typically you have 2 up and 1 down, or 2 down and 1 up. These kind of things are details that are not so interesting. What's interesting is really the fact that everything is made of this atom, and the fact that the protons are positive. That means they have a positive charge. Like in a battery, you have a positive and a negative, exactly the same thing. Protons are positive and electrons are negative. This is what we have all around us. All electrons in the world, that in the atoms of anything you can touch, are always negative, and all protons are positive. Now, before we can talk about antimatter, let's rewind a little bit to see what happened in the universe at the moment of the Big Bang. So I've made here this little you see around here towards the left, you have a yellow egg. This is the real Big Bang. This is something like billions of seconds, in which there was this gigantic explosion of pure radiation, pure energy. There was no matter then. Then, in the next millions of a second, that means a second divided in a million parts, you start seeing quarks appearing. Remember the diagram before? Quark is the smallest thing that's inside an atom, a nucleus of an atom. So this quark, starting then, within 10 to the minus 10 of a second, we're in the order of a million seconds, we saw electrons appearing. Thousands of a second, we saw the first protons and neutrons. Now remember, protons, neutrons, and electrons are the things that build up nuclear force. Meanwhile, it took about 100 seconds to start forming the first nuclei. The fastest went. This was really like a flash. The first nuclei of atoms appeared about 100 seconds, that is 1.5 minutes more or less, after the big initial flash of the Big Bang. And soon after, or rather, it wasn't soon after actually, it took 380 years for the very first atoms. So this is the period where atoms form. And we have this level at 380 somehow, by looking at what is called the cosmic microwave background radiation, we could rebuild a picture of the baby universe. So we know what it looked like and how much stuff there was in it, how many nuclei, or not really how many nuclei, but basically we had an idea of the size of the universe and everything that composed it. So we go on progressing, and after something like 12 million years, we saw the first stars appearing. But it took 2 billion years for the first planets to be created. The planets, in particular, Earth was only created about 4.5 billion years ago, talking about the solar system. And that means, considering that the universe is like 13.7, so over 13 billion years old, it took like 7-8 billion years before something like the solar system was formed. So this scale shows you how things happen so quickly and so fast within the very first second to actually build the first nuclei. It took much longer for the electrons to start turning around the nuclei and building the first atom. So that's the scale of when things happened. Here's this famous cosmic microwave background radiation, the picture of the baby universe, when the baby was only 380,000 years old. And in there we can see what were already all the ingredients that then later formed the stars and the galaxy. They were all in this picture. Don't try to understand it. Of course, this is just represented energy. Now we can say what antimatter is. Well, it starts with Albert Einstein and his theory of relativity that everybody knows, E equals mc squared, which says that energy is proportional and it can convert into mass, into matter. So energy and matter are two aspects of the same thing, and they are correlated by this famous formula. So the initial energy that we had in the yellow area of the cone before, that initial energy converted into mass, not all of it, a part remained as energy. And when it converted into mass, we can then see how much of it converted into mass. And when it converted into mass, basically gave us all the galaxies, all the stars, the 2 trillion galaxies that are in the universe, and all the solar systems and everything, and ourselves. So we come from energy. And originally we were pure energy, but then during the first second, the first atoms, nuclei and atoms formed within the next years, until this energy, all basically, not all, but a good part of it, converted into mass and gave birth to the universe. In 1928, Paul Dirac came out and wrote an equation, which I don't want you to learn by heart, but this equation basically told us that, in fact, when you talk about matter, at the same time, you're also talking about antimatter. What is antimatter? Well, antimatter is just the same as matter, but with opposite signs, opposite charge. Remember that an electron is negative and a proton is positive. Well, in antimatter, it's the other way around. So you have the electron and the positron, the electron that becomes positive, and the nucleus, the proton, that becomes negative. Now, one thing that is very important with the formula that Dirac wrote is that this formula tells us that whenever energy becomes matter, according to the Einstein formula, it also becomes antimatter. So when you generate an electron, at the same time, you generate a positron. You cannot generate an electron alone. You know, if you flash energy into, if you create, you throw energy into, like gamma rays or anything, into a surface, that will split the surface, split the atoms there, split the electron in there, and create a flash of energy that will then recrystallize into an electron and a positron. So a positron is a positive electron. So we have a negative electron and a twin positive electron. But what happens to this twin positive electron? Why don't we see it? It's not anywhere. If you look for positrons in the world, you can see any. The reason is that the positron will annihilate. It completely self-destroys when it hits another electron. So suppose I was now to throw some energy into a tinfoil or something. This will actually split off and create an electron and a positron, a negative electron and a positive electron. The negative electron, the normal electron, will stay here and will be in our world, and will eventually end up somewhere against an atom or something, and electron is what carries electricity. So it will create an electric field. It will be here. It will not die. But the positron will go and smash against the first object that it finds, even air, an atom of air, and it will annihilate against the first negative electron we find. So positive plus negative, at this level, they annihilate. You can see the reverse action when you have a positron and electron that meet, they hit each other. They hit each other and they annihilate, creating gamma rays. So basically the whole process is, if you have gamma rays, these gamma rays can then crystallize into an electron and a positron. But an electron and a positron, they hit each other, become gamma rays again. And this process goes on forever. So what happened now is that at the level of the Big Bang, back then, in the time when the universe was a baby, was just forming, there was this massive amount of radiation, of energy, that started crystallizing in all these particles we saw before, in particular in electrons and positrons. And these electrons and positrons kept hitting each other and annihilating again into gamma rays. And this process went on and on forever. If we look at a little animation, this is an animation by NASA, and shows an electron, here the green one with E minus, and there's a positron, there we go, boof, flash of energy. And what we see afterwards, well, for a split second, let me go a little bit backwards in an animation. We saw the big flash of energy, and just after, you saw that two new particles were formed, which probably would be another electron and another positron. So they can't stay alive for very long because they will keep, okay, hold on, I'm going to the next one. Now, as we said, all this matter-antimatter, electron-positron annihilation happened in the very early phase of the universe, when the universe was only a few seconds old. And this does not apply only to electrons and positrons, but to everything else. So you ask yourself, why are we here? Why do we exist? Why the universe created, if everything created annihilated again into energy? I mean, if protons and quarks and things, you know, were both created in pairs, quark anti-quark, proton anti-proton, electron anti-electron, positron, and they all ended up sooner or later colliding into each other and creating flashes of energy. Now there would only be energy in the universe. Why is there any matter? So we will have a little film now. So I'm going to move my thing to a film that I made that probably will make this clearer for you. It's I have to stop the presentation. Just a minute, I'm again still not quite familiar with this StreamYard. So here we go, and I take the window where my film is going on, and I hope you have sound on this one. Alex, are you still? Okay, hold on, going back. I've switched to the Antimatter 264 short. Here we go, and share. So hope we get sound on this. This is always tricky. Alice, can you put it on the stage? You see it? Okay, there we go. Ah, there is no sound. This is strange. Hold on, let me try to go back again. Can you hear the sound? No? Try again.
Not at the moment.
Not like it's up.
Nope, no sound. Have you got it muted on your other screen?
No, it's not. It's not muted. I can see his player's got full volume.
True.
And it's playing somehow not being somehow sound is not yeah, right with that bit. I don't think I need to do anything. It should be automatically coming. I'll just share the window. Yeah. So I'm going to try it. I'll stop the video and I'll try again. Then see if I think about. So I'm sharing screen with, and I take the window, this one, and I say share. And normally it should come with sound. I don't know why it doesn't. Okay, and now I'm going to try again. Still not.
That's a negative, sir.
No. Well, for some reason it's not. It doesn't put to send you the sound. So, well, I guess what I'll do is I'll just try to comment what's happening, because what's important here is the animation. So, right, this is a thing that says that basically, what you're saying, that we cannot understand why we exist, exactly what I said a minute ago, because by looking back into the past, you will see that at the moment of the Big Bang, there was an equal amounts of matter and antimatter. And these amounts of matter and antimatter, you know, that came from the gigantic explosion of the Big Bang, annihilated with each other. Now she's talking about the fact that a proton and an antiproton, or an electron and a positron, when they meet each other, they just disappear in a flash of energy. And this flash of energy will then create in turn other protons and antiprotons, or electrons and positrons, or anti-electrons. And the process will go on until there will be no more electrons. Now you see, this is the universe, and shows you how these little blinking stars are disappearing and slowing down, because there are no more anti-proton or anti-electron. They all have annihilated. But then why there is matter left? Why, you know, in the galaxies, in the universe, we actually don't actually find any antimatter, but just matter. So we're showing you that the life as we see it today is only due to some kind of unbalance that happened at the moment of the Big Bang, by which matter prevailed. This is a bit of a weird situation, because, you know, you can't create matter without creating antimatter. From the flash of energy, for each proton created, there must be an antiproton. And this antiproton has to annihilate with the proton. So why today do we see only matter around us? Where did the antimatter go? So this lady here is explaining what I said before, the difference in an atom and an anti-atom. And she, the host, is showing you how basically the antimatter was a mirror of matter. So you see how the dancer here has a perfect mirror image. This is what people believed, that by annihilation, you ended up with both you know, the matter and antimatter, there will be each a mirror of the other, and completely how to say, have the same properties of each other. Now, this gentleman here is Paul Dirac, or at least an actor impersonating Paul Dirac, writing his equation. And he says that when Paul Dirac, into 1928, wrote this equation, he didn't know what he had written. He did not understand why he had negative solutions for this equation for the charge of the electron. He didn't know that he had just described mathematically the anti-electron, the positron. So this was 1928, but it took like a long time until, yeah, it's now saying that basically afterwards we realized that not only the electron had the positive equivalent, but the proton had the negative equivalent, the neutron also had an anti-neutron, quarks and anti-quarks. So each single particle that was generated at the moment of the Big Bang has this sort of twin brother of an opposite sign. And then for some weird reason that we do not understand, this twin brother annihilated, and now today with some other positive one, and until today we are left with only antimatter. So this goes on for a bit now. Okay. This is showing you the 60s, when Cronin and Fitch were two physicists, American physicists, could actually find the fact that this assumption of having complete twins, that means that the antimatter will be a mirror of matter, was wrong, because they have found evidence of how antimatter behaves differently. So this is a dancer in the mirror, and the antimatter image of the dancer does not quite behave like the dancer. anymore. That's because they realized that there was a problem with the interpretation that antimatter will be a complete mirror of matter. So today, let's go back to the presentation, and I will share screen again. I'll go back into my presentation, and window, and I want to choose it. There we go. Okay, share. Now we should have back here this. The presentation should be back with, okay, with the beauty experiment. Now this that you're seeing there is an experiment that has exactly that purpose, that mission, the one of exploring the asymmetry between matter and antimatter. Why are they not symmetric like it was believed and what like the Dirac's formula had postulated? So this is one of the 4 major experiments at the Large Hadron Collider at CERN, and is placed along the collider. And basically, it's the experiment stands for LHCb, as for Large Hadron Collider Beauty. Beauty is the name of a particle that is supposed, is hypothesized to be the responsible for this phenomenon of violation of the symmetry. Now, what it says is, if antimatter was a mirror image of matter with symmetrical charge parity properties, then the universe would not exist, because it would all have annihilated, you know? The CP symmetry means that, you know, and one example I make sometimes is, so imagine that we could only have twins, male and female. So we can only make, when each time we have a child, we can only make a girl and a boy. We cannot make only a girl or only a boy. We only do that. You know, that's what happens in particle physics. Now, and after you have 10 children, you will have actually 10 girls and 10 boys, right? So these girls and boys grow up, and then 2 by 2, they meet each other, and well, and they go away and get married, right? Well, 2 by 2, you know? So basically, if they go and, you know, my girl goes married with somebody else's boy, but there will always be exactly the same number of girls and boys on Earth, because everybody can only have a boy and a girl at the same time, right? So if they all get married, in theory, there is nobody left on their own. They're all married, okay? Because there are equal number of girls and boys, and they all get married to each other. However, we find each other with a boy or a girl. So how come? Where did this come from? Can't be, because we can only make pairs. This is what is called the symmetry. Now, what happens in reality is what they call the CP violation. So the charge parity violation violates the symmetry. The fact that we're left with a boy who doesn't have a symmetric girl, it's a violation of the rule. And this was discovered in the 64 by Colin and Fitch, and it was then confirmed by experiment in this beauty experiment in 2013, 2019. What was confirmed is that there are some particles that behave in a strange way and eventually affect this production of exactly, you know, this symmetry of matter and antimatter. So there will be more matter than antimatter, or vice versa. In our universe, we have more matter. That's why we exist. But this is still under, you know, they're still trying to work out what exactly happens at the moment of creation of matter and antimatter. So another experiment that is interesting to mention is AMS, the Alpha Magnetic Spectrometer, which was also built at CERN, but it's an international collaboration. And this has been installed, is a spectrometer installed on the International Space Station. And what it's doing is like a big antenna, and it's trying to find antimatter in space. Because some people believe that the antimatter is not gone, it's still there. You know, our equivalent of our universe, what we see in matter, but it could be at the edge of the universe. So they're trying to see if they receive any antimatter particles that eventually travel through your universe and arrive on Earth. So far, they haven't seen any evidence of large amounts of antimatters being anywhere, hiding in the universe somewhere. So yeah, this is what I just said. No results to date. So at CERN, what we do as well, in order to be able to study antimatter, you understand that what happens with the Large Hadron Collider is that we can generate, by colliding two protons together, we can generate pure energy, which then crystallizes in other particles. By studying this process through this detector, which is these giant cameras that can take these pictures for things that happens in billionths of a second. You know, imagine the shutter time. These are not real cameras; they're electronic detector. They can rebuild these event generations of particles due to electronic data then processed by computers. Now, but the time is so short that sometimes we don't have enough time to study antimatter. So in order to study, we decided to make it. And at CERN, there is a factory of antimatter where we actually take protons that are accelerated near the speed of light for the collision, and we slow them down. For this is not an accelerator, it's a decelerator. It's something different from the LHC. It's much smaller. And these magnets actually, they slow down this anti-protons generated by the collision proton-proton. We take antiprotons generated and we slow them down until we can catch them in a bottle, which is not exactly a bottle, it's a trap. And in this trap, we try to build atoms of anti-hydrogen. So we try to fabricate, to build antimatter. As we said, a hydrogen atom is simply made by a nucleus that contains a proton and one electron. Now, what we're trying to do is to put an antiproton instead of the proton and the positron, which is the anti-electron. So instead of having the proton positive and the electron negative, in the anti-hydrogen, we have the opposite. We have a positive electron and a negative proton. Now this trap, let's say in this little, I think, yes, I have a little animation that will show you how the atom of anti-hydrogen that we have built by getting positive electrons to rotate around the, you see, these positrons are increasingly, they're put in oscillation using microwave fields and kept there by very strong magnetic fields of the level of 1 Tesla, which is a very, very strong magnetic field. They then are injected into a cloud of positrons, of positive electrons. That will then start, see how the positive electrons eventually start turning around the proton. And therefore, it will form an atom of anti-hydrogen. So let's, oh, there it is. Okay. I think it's showing you again what happens. Yeah, if you look at the bottom, there's a kind of a little bathtub with a ball that moves inside. Well, that shows you how this thing is kept. This bathtub is a magnetic field. When we release the magnetic field, the atom ends up against the walls of this trap, and it annihilates with the matter that it finds on those walls. When it annihilates, it creates these parts, these new particles that will run in different directions. So, and this will tell us that we are generating, because when we generate anti-hydrogen, we can't see it, you know, we cannot see particles. We can only detect it, and detect it means that the particle must hit a surface. So when the particle finally, we release the magnetic field that kept it, I go back a little bit, when we were in the bathtub. See the little ball here is moving, again I start the animation, the little ball is moving in this bathtub, in this magnetic field, you know, and is kept there. Until we release the magnetic field, goes against the wall, annihilates, and becomes a flash of energy, and then generates new particles that we can detect. At this time, we knew that we had anti-hydrogen. This is how we, you know, in order to trap it, you have to kill it. That's the idea. To study, you have to generate it, to create it. and to detect it, you have to kill it. So how does antimatter interact with us? What is it used for? Why do we build it? We build it to study it. And once we study it, we can actually make applications. The first application that, actually impacts our life directly is on the medical fields, like many of these applications are. I told you last time that was a couple of times ago, I told you that, for instance, the CT scans, the MRI, magnetic resonance, were inventions coming straight from our detectors. So they started at CERN. And today we are curing cancers, brain cancers, by using proton beams that are using the technology of the Large Hadron Collider, of any collider, of our particle accelerator. The same particle accelerator that we have, on a large scale to study these interactions of particles hitting each other, the same ones, but in a smaller scale, are in our hospitals. And they allow us to do what we call the radiotherapy and hadron therapy, proton therapy, which basically consists in shooting a beam of protons or other particles inside the cancer and destroying the cancer without going to touch the tissues around it. It's a high precision operation, but it works. So the positron emission tomography, PET scan, you probably have heard about it, is a much more precise than MRI and CT scan, and is allowed to, for instance, even depict, here, for instance, is a brain. You see, in the brain, there are these color areas. These color areas not only can diagnose diseases like cancer, they can diagnose Alzheimer, things that you cannot see with the normal MRIs. So, and they can, Parkinson, Alzheimer, or even some psychotic conditions. They've even been used to be able to determine if a patient who is in coma is actually still thinking. And they have done this. For instance, when you are scared, or when you are excited, when you're relaxed, your brain works in a different way, generates in different areas of the brain become active. So this color shows you which areas of the brain are active. And this means that if you put one of us, a person who can talk, me, you, test subjects, into a PET scanner, then you can show him, some relaxing images, film, relaxing music, relaxing flowers and nature. And the PET scan will get certain colors, say like blue or pink. Then they show you some scary stuff, dinosaur that's eating you, Jurassic Park, and the image they see is something more like red or, yellow, whatever. The doctors know what to do. So basically, you can tell from this picture the emotional state that you are in. Then you do the same thing to somebody who's in coma. And if they react the same way, then you know that they actually are receptive. Well, it's just one to explain why PET scan and how much more powerful it can be than the normal MRIs or CT scan. This, for instance, is a scan, a full body scan that can be used to diagnose very early cancers. This was COVID. Here you see the viruses, where they are concentrating. And this is because they were trying to fight COVID exactly there where the virus was accumulating. They could actually do injections of beta-metasone, whatever pharmaceuticals, exactly there where the viruses were concentrating. So this is so precise, it can show you virus concentrations. And, cancer, like breast cancer, this is a very, very accurate detection. They can detect breast cancer really in the very early times, therefore saving a lot of lives. So that's what comes straight out of antimatter, because PET stands for positron emission tomography. Positron, remember, is the positive electron, the antimatter part of the electron. Now, you probably have seen the film Angels and Demons and or read the book, and that's when Dan Brown came to CERN. I actually met him when he was at CERN because he was exploring all the different subjects for his film. And this book, is a fiction book in which some the Illuminati, whatever, and was a killer sent by, well, I don't tell you what the story was because I don't want to spoil the ending if you want to look, but some killer comes to CERN, kills a guy who was named after me, by the way, Silvano, in the film. Well, he kills because he was the guy, the scientist who created the antimatter experiments, the antimatter bottle, and he steals this antimatter bottle because he wants to drop it on the Vatican, because antimatter would have the most destructive property ever. This would be the bomb, the ultimate bomb, antimatter, because 1 gram of antimatter could probably destroy like half the planet or something. At least I think it was like half a gram of antimatter that was in that bomb, in that bottle that the guy stole from CERN. Now, just to tell you, the real antimatter bottle that we have at CERN weighs about 3 tons, and it's about 3 meters long, steel, pure steel, with huge magnets around it. So it's not something you can put in your pocket, really. Anyway, that was, and as soon as you take it away or detach it from the electricity, well, it just immediately dies and the antimatter goes. Besides, the antimatter, our antimatter factory only could generate something like 380 atoms that can last for 17 minutes. 380 atoms are really very far away from half a gram. They're absolutely nothing. So, and like the military have been looking at antimatter to say, oh, we can make a very big bomb. But this would be an extremely expensive bomb because 1 gram of antimatter would need $62.5 trillion to produce. This is the amount of energy of electricity you have to put into generating this anti-hydrogen. And it would take about 10 billion years to generate that to something like our antimatter decelerator, our antimatter factory. So we really generate a few atoms, which are absolutely of no power. When they are against the walls, if it wasn't for very sensitive detector, electronic detectors and computers, we would never know it because it's nothing absolutely. I mean, this light that I have on my face is doing more damage to my eyes than any amount of antimatter we are generating that could do to anything at all. So this rules it basically out of a possibility of using it for making bombs or anything else. Besides, why do they need that? I mean, they have like 10 times, 100 times what they need to blow up the whole planet, in terms of nuclear bombs. They certainly don't need antimatter, especially at those costs. And then, well, you all know about Star Trek and the Enterprise, that uses antimatter engine for interstellar propulsion. Now, will that ever be a possibility? We never know, but maybe in the future centuries, they will probably find a way to use antimatter for interstellar propulsion that will make a spaceship go on forever throughout the universe. So, and that concludes my little presentation. And so I now open the floor for questions. So, Alex, if you can remove the presentation and.
Well, that was quite enlightening. And so, if you don't mind, and I appreciate you having me here, sir, I just want to say that up front. Okay. So a few things I want to ask you. The particle or wherever the Big Bang stemmed from, okay? Is there a
yeah?
Okay. How it started? Is there a fear that could be replicated and actually cause the destruction of Earth? Is that a possibility?
Well, I can see it. I can think of about 10 different, much more realistic possibilities of destroying the world, from climate to nuclear war to, who knows what else, to asteroids falling on us, etc. No, well, the Big Bang, we have no idea how the Big Bang came to be, what was before the Big Bang. But the Big Bang was a gigantic explosion in terms of, well, not even quantifiable, gazillions of let's say, electron volts. I don't know how you want to describe the amount of energy was like absolutely absurd that formed the whole universe. At CERN, we're trying to reproduce the same thing by colliding one single proton against one proton. They head-to-head collisions and create a micro Big Bang that, in a way, will reproduce the same the same environment of the Big Bang. That means a big flash of energy, but big at the level of my explosion of energy will then regenerate other particles that we can study. And by looking at this process, we can understand how energy transforms into matter, matter transforms into energy. The energies we are talking about, from this gigantic machine, that's the LHC, 10 kilometers diameter, 27 kilometers around, circumference, 100 meters underground. And this whole machine has huge magnets that will use a lot of electricity to keep this beam of particles together and to turn them around its circumference until they collide. And they collide 40 million times a second, So every second that the LHC runs, we have 40 million collisions. I mean, these beams meet 40 million times a second. So right now, as we're talking, every second of my talk here is 40 million other collisions that the thing is having. So as you see, nothing is happening. We're not being destroyed. The world is still there. And that's because, now imagine a lightning. Imagine the strength of a lightning. Yeah? You imagine what happens to you if the lightning hits you, right? Now, take a battery, take two wires, and touch them together, okay? And look at the spark it makes. Will that spark kill you? I'm not talking about even that battery. I'm talking about one of these batteries, right? Take one of these batteries, put two wires there, and touch the two wires, and make a spark. Is that going to kill you? No. Because it's a matter of size. It's a matter of quantities, right? The Big Bang or the lightning have a huge amount of electricity and a huge amount of energy, and they kill you. The particle collisions at CERN, whether it's antimatter or whether it's proton-proton in the LHC, have the power that is 1 million times smaller than the one of the battery. Is that going to kill you?
Yeah, no. So basically, all right. Would you agree that space would have had to exist for when the Big Bang happened? For it didn't just, space wasn't created at the same time as the Big Bang happened. Space was already in existence. Would you agree to that?
Okay. First of all, well, it depends on the theory you're on. If you follow Einstein and the theory of relativity, then space, for a start, is not space, but it's space-time. It's the same thing. Space and time are the same, continuous, and they are related by the famous formula. Just like energy and matter, energy transforms into matter, matter transforms into energy. Space-time is some equivalent concepts. That means when you go into the speed of light, space will become shorter and tend to zero, and time will dilate and turn to infinity. So this is all included in that famous E equals mc squared. Now, what happened with space-time at the moment of the Big Bang? Well, according to, if you want to follow Einstein's theory, and quantum physics, it was created at the time of the Big Bang. And as the universe inflated, imagine this balloon that you're blowing, and it inflates. That's what inflation of the universe really is. Time dilated, space-time. space-time dilated and filled this universe, and it keeps expanding and expanding and expanding, and space-time is also expanding with the universe. And we have no idea what's outside of our bubble. We can only see what's inside our bubble. With all our telescopes, our radio telescopes, and we cannot see outside the universe. The boundaries of the universe are fixed boundaries, as well as we cannot see what is before the Big Bang. We could have no idea. We can only have theories, hypotheses. Some people have theories that, because not all physicists agree on these terms of what was before, what was after. So what they define, they don't talk about the universe. The universe is only our little bubble, right? There may be many, million, infinite universes, in something called reality or cosmos. So the cosmos is something that goes beyond the universe. The cosmos is it's everywhere. It's outside. And our universe could actually be one little ball in this, together with millions of other universes. So,
sure.
I have a bit of an agenda. I think that I would like to first speak better more deeply about the Einstein general relativity, what is gravity. Then we can go into things like a little bit of quantum physics, and then go into multiple dimensions, string theory, etc. And multiple dimension is what, a lot of physicists today believe is the cosmos. If we only want our universe without 2 trillion galaxies and probably gazillions planets, is only a dust speck in something much bigger of infinite, that is the cosmos.
Okay, so I'm glad you brought this up, because now this is going to get into one of my other questions. So I heard you mention something about gamma rays being produced. Do you remember that part of your talk there? Can gamma rays open up a hole in space-time?
Well, okay. Now, what are gamma rays? Gamma rays are ordinary rays that we use mostly also in medicines. We use gamma rays, or what have you heard about gamma knife? That's used to operate your brain. They shoot gamma rays inside your brain, and they can kill a tumor, a cancer.
Yes.
And so this is in every well-equipped hospital. You'll find the gamma ray machine. But gamma rays are just a radio frequency that is of a certain wavelength. So it's like microwaves in your microwave oven. Is like light. It's like the radio waves that make the radio, television talk. So it's just one frequency of rays. So basically, what happens is that it's are generated in. Okay, we can see in many galaxies. We can see gamma rays being generated out of black holes. So some people believe that this could be that there was some matter-antimatter annihilation happening as our matter of our universe falls into the black holes. It's attracted by the black hole, which is this object of extremely high gravity that can suck in entire stars and solar systems, which are at the center of all the private galaxies. That this black hole, while they suck matter in, this matter could actually end up into another universe, which would be an anti-world, an anti-universe, a universe of antimatter. So as our matter annihilated with the antimatter of the other universe that was on the other side of the black hole that would function like a portal, at that moment, the matter-antimatter annihilation creates gamma rays. And we see these gamma rays sprayed out of our black hole. They must have gone, the stars that fall in there must have ended up in an antimatter universe. That's why now we see the gamma rays coming out of our black hole. Well, that wasn't the idea that as matter falls into this black hole, it gets disintegrated. So when our sun will fall there in about really we will fall into the black hole.
We hope. We hope.
I guess I'll be still to experience it. It's not a theory. The point is when matter falls there, it disintegrates because the gravity is so high that it completely fuses the atoms, and so they disintegrate into a nuclear collapse. And this generates, of course, all sorts of rays, including gamma rays. And gamma rays, the energy is so high that they manage to escape the black hole, but they only can escape it if they are on the event horizon. That means they are outside the edge of the black hole. So matter is disintegrating not when it falls in, but when it's about to fall in. And they can still escape. You know, the black hole sucks in even light. But once you're in, light cannot escape. But if you're on the edge, on what we call the event horizon, then there still can be an emission of gamma rays coming out of there. I don't know if they're asking your question, but that's what.
So okay. So I understand the whole concept of the imploded star and the black hole situation. Now, obviously, if that's the case, wouldn't you say that a black hole is the expansion of space-time in a completely different direction? And if that's the case, if that's the case,
Right.
What could you use? What could we study to repel the gravity from imploding matter to maybe travel through a black hole into another known section of the universe? Is that possible?
Okay.
Is that a possible?
Yeah. But black holes, there's a that's of course not supposed to be done by Stephen Hawking, not the material with a big physics. But one thing is for sure, we still cannot know what exactly happens in a black hole and behind the black hole. Now, as you would see when I would talk about Einstein's general relativity and the space-time continuum, every object with mass, with a certain, any mass, even this pen, every object with mass will create a dip in space-time, will basically warp space-time. Massive objects like planets, we create a bigger warp, a bigger ball. It looks like a ball, like a ball, in the same. Objects coming actually, be orbiting around it. This way, you see, for example, why does the comet orbit around Earth or around the Sun or other? Because Earth is making its own little ball in space-time. It falls into this ball, and so when the comet comes, takes the edge of this ball and turns around, then it gets detected out, depending on the speed it has. If the speed wasn't that high, then it would start orbiting like the Moon does, and like we orbit around the Sun. Trapped into this ball, we orbit around, and it's a we call it a spiral orbit. Every year, there is a double force. There is a centrifugal force away, but then there is the attractive force of the ball, which keeps you in. So slowly, like the moon will be falling on Earth, and Earth will be falling in the Sun, etc. And the Sun, like the other Sun, will be falling into the black hole. Because the whole universe, the whole galaxy that we're in, turns around the black hole. Now, what happens when you fall in? Well, the stars that fall in, of course, we have no idea. By the relativity, we have to think that because the black hole makes such a huge warp in space-time, this warp, it becomes almost not a ball, but almost like a cylinder, and it goes down so far that becomes almost cylindrical. But when you fall in there, you get attracted to the thing. Now, what? Hello.
I lost his audio.
Yeah, some internet problems. Am I back?
Oh, no.
Hello?
Yeah,
You are
you're
back, sir. You are back.
I'm back? Yeah, okay. So what I'm saying is that this could be like a bottomless pit. And some people have thought about, one of the theories is that if this is space-time and you have a black hole here, and this black hole will make, now imagine, a very long pit under this paper that will go down like this. And it could be so long that it could warp space-time. So that if you have, I'm going to design here two black holes, one here, one the other side of the universe. Can you see my two spots that I made there? Right. Now, each one
Yep.
makes a very, very long ball under it, and this is able to warp space-time to the point that they coincide with each other. So, if you go into a black hole, you may come out of the other.
Right.
See what I mean? And this is what they
I
call
do.
tunnels. Space-time tunnels. Now, does this exist? It's theory. We don't know. Now, mathematics
Wormholes. What we call them as wormholes.
Sorry?
I said, would a lot of the people know them as wormholes?
A wormhole. Well, the problem with wait a second. I've lost sound here. I'm trying to bring it up. There. Okay. Sorry. Well, the problem is that even way before you fall in, you're already dead. For a start, the gravity would be such that the planet, imagine planet Earth, I'm talking about, 2 light years away from, we are here at 30,000 light years from the central hole. But imagine we're at 2 light years. Well, planet Earth won't be a planet anymore. It will be completely oblong. It will be, the atmosphere will have gone, sucked in by the black hole. We would be, if we will still be alive, all of a sudden you snap your fingers and you're there now, I would probably weigh something like 600 million tons, which means that I would be crushed into atoms by my own weight. And when you get close to it, we disintegrate. Nothing can go through a black hole keeping its atoms together. The atoms will be crushed in by the enormous gravity, become pure energy. What comes out of the other end, if there is another end, is only a dash of light, which then will crystallize into new particles, into the new part of the universe, or into the other universe, wherever we end up from the other end. But there's nothing alive that can go through that. Not even a stone can come in the other side together, being still a stone.
So, okay, so here's the question for you. As the LHC was being built, or some of the applications that were going to be researched, was anything that they were doing or planned on doing a search for, I don't want to call it time travel, let's call it revisiting certain spots in time?
Yes.
Was any of that?
We are very far from that. What I mean is, we wish we could say yes, but time travel is part of a theory, again, that is linked to Einstein's theory. And one simple way, we all traveling into the future. We are today traveling into the future. Yesterday was yesterday, tomorrow is tomorrow, and tomorrow is the future. So every day we pass, we go into the future. Now, if you're talking about instant time travel, that means now today I want to shoot myself 50 years from now, with my own body like they do in the science fiction films. Well, that is something that is conceivable if you could travel near the speed of light. Because, like I said, time slows down and space increases. We know when they did the test, with the two twins, the twin paradox of Einstein. Well, I'm going to talk about all this during a specialized day on Einstein. But basically, you probably heard about the twin paradox. If there are two twins, one who stays on Earth and the other one that goes on a rocket that goes very close, I wouldn't say to the speed of light, but it was very, very, very fast, something like 100,000 kilometers an hour. When this second twin comes back to Earth, he will be younger than the other twin. So in a way,
Yes.
so you know what I mean? That's the paradox, is the fact that time for him passed slowly. So if a year has passed on Earth while the other guy went out to space and came back, maybe for him it was only 3 days. So he was only 3 days older than when he left, while I'm a year older. So this is how time messes the story of, and the travel in time, you see it in this way, but it only works in the future. Going back in the past, the theory does not formulate that. So time travel in the past is today not like a theoretical possibility within the Einstein, within the general relativity. Now, what I was going to say though is that we are exploring matter, energy, the conversion, etc. And what we find sometimes is completely, different from the expectation. Like, the story of the antimatter. They all believed that antimatter was totally symmetrical to matter, and they couldn't explain why we exist, why we annihilated. Until somebody, like 30 years later, demonstrated that it was a wrong assumption, that the theory was wrong. That, in fact, there is a phenomenon called the CP violation, the charge parity violation, which violates the symmetry. So we don't know it all. The theories, they formulate a theory based on mathematical deductions, but you need to experimentally prove those deductions before you can say it's true. And this is what the Larger Than Collider is there for, and all the physics experimental labs, to validate this theory. We succeeded with the Higgs, Peter Higgs in 1965, so that of this boson that would transform energy, or rather give particles a mass. And this was out of his formulas. He just calculated, made all these calculations based on quantum theory, based on relativity, and he came out to this conclusion that there must be this particle that gives, I would say creates matter. Nothing is created, but assigns matter mass to passing particles that traverse something called a Higgs field. Now, this took 50 years to demonstrate. I was there. I actually interviewed Peter Higgs at CERN when we announced that we have found the Higgs boson, the thing that he had hypothesized 50 years ago. He was in tears. But the thing is, he was in tears because it was so moving for him that he had seen this. But it takes 50 years minimum to validate a theory. Now, I believe that we are extremely far, not mere 50 years, we're probably hundreds of years from anything that could have to do with time travel or with black holes or with, of string theory. That's theories that are so far-fetched and so far away from the kind of tools that we have today.
Well, to say that one, okay, I'm going to try to word this here so it doesn't come off condescending or anything of that nature. But to say that large amounts of matter can be produced from a single point in a Big Bang theory would sound just as far-fetched as the idea that traveling in time would be. Do you understand what I'm saying? So I think that I think that if it's to say that the Big Bang was possible, I don't see that how time travel could be also dismissed as being impossible when you have a single particle that created a huge amounts of matter and mass out of a single point of. Did you see what I'm saying? Does that make sense?
Yeah. We don't know what created the Big Bang. Certainly, it wasn't one particle. It certainly was. The current hypothesis is that it was a very concentrated mass. Imagine a black hole, that is squashed into something like a football. And so the particles in it, the zillions of particles in it, are very, very compressed. Now, you know that there is something called the strong force, and the strong force is the strong nuclear force. It's the force that keeps the nucleus together. And if you try to stretch the nucleus or you try to compress it, you need a huge amount of energy for doing that. But this is what happens in the sun. The sun burns. Why? Why does it create so much energy, the sun? It's because it's squashing atoms. The gravity in the sun, because the sun is so big, that the gravity of it, it is squashing the atoms, setting them on fire. Because when you squash the atoms, you are fighting the strong force. And what happens is a fusion. You are fusing the quarks inside the protons, and the whole thing gets fused into pure energy. So there is this theory that believes, called the Big Crunch, and that is that the universe, starts with the Big Bang, then it expands and expands and expands, and it becomes so huge as it is now. And then at some stage, it will start. Gravity will bring it back together into something that will be so massive and so small that it will explode again and create a new Big Bang. So they're talking about this accordion kind of thing, that the universe expands and then it will collapse again and then it will expand again. But this Big Crunch theory has lately been demystified because we have noticed that the expansion is accelerating. So instead of, a firework where you start with a bullet and it goes boom, and then it slows down. And now, typically in a firework, the sparkles there, they will fall down on Earth again because there is the Earth gravity. But if you shoot a firework in deep space where there is no gravity, what happens? That the sparkles will then go boom, and they go off forever and ever and ever and ever. So this Big Bang, where of course it wasn't going to fall. So all this mass, this matter and energy created started, being projected out. Then people say, oh, at some stage it will stop, and it will then the gravity, when the initial energy of the initial velocity, speed, has finished. Now there is a gravity that will attract them together, and they collapse again together, right? However, we're noticing something that goes completely the opposite way, and that is that it's gone there, and now it starts accelerating. What is like something was pushing it apart. And this accelerated expansion is believed to be due to what we call the dark energy, which is the majority of the stuff.
We did lose you, if you're able to hear us.
Looks like we've lost Silvano for a second. We'll give him a few seconds if he comes back.
Oh, of course. Absolutely. I find this topic very enlightening. I've done quite a few videos on this very topic before.
It's interesting. It's always interesting to see how the science. Oh, we're back.
I think I'm back. Am I back? I'm sorry. I have to keep reminding you. I go for a walk. I have to keep reminding you that I am on a dot of an island of 30 kilometers wide, 40 kilometers wide, in the middle of the Indian Ocean. And so, internet here is, a great when it's there, but sometimes it's not. So, sorry about that.
Yeah.
Anyway, yes. Sorry, you were saying that is inconceivable.
Okay, so and here I think I want to ask a question that I think a lot of people have had, and a couple of the things that you said is we just don't know, or we have no idea what will happen. Can you understand a lot of people's thinking of that when people start saying that are in the position of doing these experiments, and they're like saying, well, we just don't know, or we don't know what's going to happen. And then people are like, well, then God, man, don't do it. Don't do it. If you don't know what's going to happen, do you see how the fears could be in someone's mind?
No,
when they hear things. Okay.
Let's not be thinking. We don't know what was before the Big Bang. We don't know what will happen after the universe expands. We don't know what's in a black hole. We don't know what's in a human brain. How does the brain work? We don't know that. We don't know a lot of things. We don't know how to defeat completely cancer. We didn't even know how to defeat COVID-19. So what I mean is there's a lot of things that we don't know in the science, but we know our engineering. You know, what you're saying is exactly what they told Edison when he was going to light his light bulb. Don't do that. The whole world will explode if this bulb goes on. You know, they thought when the time of Tesla, I don't know if you saw the films about Tesla and Edison, etc., about whether they were going to use continuous current or alternate current, you know, and everything. And what they
I saw the whole thing about
Edison, yeah,
Westinghouse and Tesla.
Edison went around saying that if we were to use alternate current, like Tesla was proposing, then we would all die electrocuted. That would be the end of mankind. Electricity was a huge danger, you know. You know, that's the kind of thing. But luckily, back then, like now, engineers know how to build stuff in a way that is safe. If you knew the safety, can you hear me?
Yeah. Yes, I can.
Well, I was saying, if you knew the safety regulations that there are at CERN for building anything, you know, I mean, that's absolutely, we don't take any risks because we live there with our children. You know, our families are there. We're not some kind of ivory tower scientist, mad scientist like Frankenstein. We have normal people. We play guitar. We do rock concerts. We have children. We go skiing. We you know, we're just like you, and we don't want to die. So we would never do anything that we're not 100% sure that it's not going to do anything nasty. And, you know, one proof was the fact that, CERN is going to make the black hole that's going to swallow the world. We knew very well what we were doing. And if we do actually build a micro black hole, that would actually tell us a lot about what's happening in the black holes, because we have a micro in vitro version of a black hole, so we could study it, you know. And the thing is, there's absolutely nothing dangerous with that. One of the things I tell all the time is think that the energy of the collision of the protons is then of 14 tera electron volt, whatever that could mean to you, 14 billion, 14,000 billion electron volt, right? That's the energy. Now, I am being traversed every second by about 100, 200 cosmic rays, which have a voltage, a power that is about 1,000 times that. It's not 14, it's 14,000 tera electron volts. And that happens all over the world, all over the cosmos. So if the protons can create a micro black hole, those particles, the cosmic rays that fall through us all the time, generated by supernovas and by the sun, etc., these cosmic rays would have generated these black holes, a million, zillion, gazillion times before us. And the whole universe would have been disappeared in the black hole. So what we're doing is a very, very small fraction of what's happening. Again, the story of the lightning and the sparkle of the battery is the same thing. We're doing the sparkle of the battery, and everywhere in the universe there are lightnings, and yet we don't die.
Have there been any experiments that have took place there that had unexpected results?
If by unexpected results mean, things that we didn't expect to find, yes, LHCb, the beauty experiment, found some strange particles called the pentaquark and the tetraquark. As I showed you before, inside a proton or a neutron, there are 3 quarks. And now they found this new particle that actually is a sort of double particle. I mean, no, a new particle that has 4 quarks inside. And another one, there is a double particle that has 3 on one and 2 on the other. So it's a composite particle called the pentaquark, or 5 quarks. So there are different animals that come out of that machine, let's say animals. And we call it a particle zoo, because there's so many, there's about 100 and something, 14 particles that have been found so far. But we keep finding new ones. And the new ones that we find are good because they show us new ways of understanding physics and new opening doors to what we call the new physics. The new physics will be the one that eventually would give us things like, like you mentioned, like anti-gravity, or I don't know, you talk about time travel or something like this. Whatever, for the time being, with the physics we know, we can do that. But we never know. That's how a scientist must be humble. He must never dismiss things, say, oh, that's not possible. No, nothing is not possible. Things are more or less probable, you know? And sometimes things are just, you see them impossible because you start from the wrong assumption. You start from the fact that you don't actually know everything. And to know more stuff, you need to experiment. You need to do these tests. But the machines we use for experimenting are 100% safe. If we say we're going to do this, and there's not going to be any destruction of the world, there's not going to be any nasty effect or anything, we know it because we know what we're doing. We've been doing this for 50 years. It's, much more, because CERN is from 70 years. Sorry. It's, CERN is 2 years older than me.
So I got...
when I was already doing, and they haven't destroyed anything.
Well, I think I have 2 more questions for you, and so let's put Dan Brown's his antimatter fiction out of the way here a second. What applications do you believe antimatter will benefit the human race or humanity, is from not just these experiments, but in the creation of what benefits will we see due to these discoveries?
Well, you're talking about antimatter specifically. Like I said, the PET, positron emission tomography, is something that doctors are using more and more, particularly brain doctors. And today it's very expensive machine to have, so it's only in very large hospitals. There's another factor to that, is that the liquid they inject into you has a lifetime of only, I think it's 6 or 8 hours. So it must be produced and injected to you within 6 to 8 hours. So they cannot, for instance, send it to the, because it takes 10 hours to travel from here. So the liquid would already arrive expired. Now, that's a parenthesis on the PET tomography. But like MRI used to be very, that also was invented itself. MRI was like a very expensive machine at the beginning. Now today you find it in every hospital and even in private radiology labs. Used to be something you found only in big hospitals. Today, there's X-ray labs everywhere in the corner of the building there are. So this is being democratized, and we will keep inventing new machines. We are working on this hadron therapy, which is the possibility of shooting and we do it. Daily we save children's lives, because children with by injecting protons into the cancer, and these are so specific, go through your body. But they are particular radionuclides. They can explode exactly at a millisecond after being. It will go to the skin, it will go to the flesh, it will get to the brain, it will go to the brain without even touching it. Like glass, like. But then, particular cancer, boom, it explodes and destroys the cancer. These are that come straight from the technology from detectors, from what we have. No, are invented by certain people. So then start the research group and
Okay.
so this is, I mean, the medical stuff is just one of the sides. Yeah.
Okay. I did. Yes, in your presentation, I did the PET. So I did get that, and I was just wondering if, for the cost of these experiments in creating antimatter, I would think that there would be more applications intended
Well,
than just.
Yeah. The figure I gave you of like 64 billion, that was if you want to generate a bomb out of it. So that's why it's
No, I know. I got it. Yeah.
But we only generate a few atoms. We have 300 atoms. That is nothing. Not even a droplet, nothing, not even a gram. We're to the level of picograms. That means millions of a gram, and that doesn't require that much energy at all. The particle decelerator actually doesn't take much electricity at all. I mean, this has been, think about something. CERN has a budget of $1 billion a year, okay, which is given by 22 member states. So for each member state, it's only a few $1 million. But CERN has given the world Wide Web. It's given the world MRI, CT scan. It's given. There is the machines that are at the airports to scan through the luggage. They also use, some kind of particle detection. They can scan entire trucks to look for, or containers. They look into the containers, and you can tell if there are Chinese people stuck in there, something like that. So all the things come out of a budget of $1 billion a year. The American defense, spends that in 10 minutes of war anywhere in the world, right?
Yes. Yeah.
And what benefit does that give to mankind?
Absolutely none, sir. Absolutely none. I think that if they spent that money on something more altruistic rather than destruction, I think this world would be a whole better place to live in.
Exactly.
So the last question I have kind of has come in two different sections. Okay. So obviously, you said you haven't held the position that you've had for 11 years. Did you have to sign, or did you have to agree on a non-disclosure about any of the experiments?
No, there are no secrets. There is no such thing as classification. That's stuff that only exists with anything that has to do with the American government or with armies. At CERN, there is no research that goes into anything that can help an army. So in CERN, we even today, we have Russians and Americans working together. We had them during the Iron Curtain. Because there are no secrets, this is really understanding the basics of nature. There is as much interest in CERN from the point of view of secrets and armies and whatever, or CIA, as there would be in finding out the life of deers or certain fish. I don't know, discovering a new fish in the deep ocean. Absolutely no interest for that, So we are trying to discover new fish in the universe, and these things only tell us about our origins. CERN is no secret because we have the whole world working there. There's 22 member states plus absolutely every other state in the world. There are more than 250 nations that are working in CERN in the experiments, and they all share the same data. They do shifts, and every shift, a night shift, takes the data from the day shift, and they all work together, sit in front of the same computer, have the same login. There are absolutely no secrets. That's why I don't have to firm an NDA or anything, because I can tell you what we know, because that's all, it's global knowledge.
Okay, so the last part I got to that two-pronged question is this. So obviously these are government unified project going on there. Did you notice any private sector involvement? And I'm talking, and here, let me ask it like this. And I know it's going to come off sounding crazy when I say this, but we were talking about Dan Brown's Illuminati aspect to the CERN fiction storyline. Did you notice any high involvement with any kind of private group, or shall I say, I don't want to say Illuminati, but I want to say.
Yeah, I know what you may be hinting, like, this story of the Shiva statue there. Is that what you're talking about?
Oh, that's a little part of it. That's a little part of it.
Right. Right. Well, that was a prank that some idiot students did for fun to share between themselves, between their and their friends. Say, oh well, this weird spooky statue. Let's make this ritual. That was students. So there are students, about a few hundred students every summer. I was a summer student in '76. I spent 3 months at CERN doing my thesis work for my master's degree, and so there are all the students there. And students, they want to have fun, right? So they thought that was fun thing to do, idiots. And, of course they were told off for it after the thing went viral. There's nothing like that at all, There's nothing, the people who say, well, mystical stuff or anything. No, there is, you see, at CERN, there is no politics. There is no religion. That means everybody can keep their religion. At CERN, you will find Palestinians and Jews partying together. And today is Russians and Americans, the partying, they organize, they make disco parties, and they go there because we're all friends, because there is no particular, the only groups that there are clubs. I started a music club at CERN, and I started a festival, a yearly festival, and we made rock bands and things like this. There is the diving club, there is the car club, the ski club, there is the cricket club, the rugby club, whatever, you name it, they have all the clubs. That's because it's it's a tight international community where we have a lot of hobbies, a lot of activities. But that's nothing like you want to think sects and stuff like that. Nothing like that at all.
Well, I was kind of, and it wasn't so much that ritualistic prankster stuff. I was talking about, I was just wondering if there was some kind of private group monitoring your progress or taking an unusual interest in the activities that were taking place there. Like, as I said, I mean, what is your whole thought about the Illuminati? Do you believe it's a real thing?
Well, no, the Illuminati was a real thing back in 1700, and Dan Brown took his idea, back then. And then now today, of course, after he did that, maybe some idiot out there think, oh, let's pretend to be the Illuminati. Let's make a website now. We are the Illuminati, and they created the Illuminati now because they can show off, I don't know, and make their own ideas, or the bee becomes scary to everybody. But I mean, for us, it just made us laugh. Dan Brown, when he did this thing, and he did this, wrote this book. I don't know if you read the book or saw the film, but in the book, like 1/3 of the book happens at CERN, and everything is very different from what CERN is like. There was a wind tunnel where physicists were, I don't know, spending their lunchtime having fun in a wind tunnel. Yeah, well, right, we don't have that. There was, I don't know what else, but CERN was looking very, very different from what it actually is. CERN looks like a university, like a campus, and there it looked like some kind of moon base, Mars base, or something like that in the book. But then when he sent us the prototype, he did after being at CERN, he spent a week or 10 days at CERN, visiting all the different labs, and I was one of the experts that took it back. Then he sent the book to us, and said, remember, it's fiction. That's what was written on it. And it is fiction. That whatever he wrote there is
No. I agree with you. That's why I was kind of I was really hesitant on using the word Illuminati. So you know what I want to do is I want to leave you with this. So a lot of people out there, a lot of people have viewed the Swiss Goddard Tunnel ritual ceremony that took place. I don't know if you're familiar with it, but as you can see,
I saw it after Ian mentioned it. Yeah. A few weeks ago.
And
it's very
you can see how people would look at that and go, something weird is going on, and it doesn't seem like any of the elites that were in attendance even questioned what they were watching or what they were viewing, because they already had an idea of what was going on. So I'm in a position like, you know what, when we don't know what's going on, we need to ask questions. So that was one of the reasons why I wanted to be here today, to ask the questions for the people who don't get a voice. So you can see what my whole, thank you. Sorry about that. Go ahead, sir.
I totally agree. I saw this a month ago, the first time that we had discussion. Know about that. Because I wasn't there. I've been here. Anyway, when I went to look at that, I mean, what a crazy thing they did that. But I think I understand what that is. Well, first of all, the Gotthard Tunnel is in Switzerland. Now, CERN is in the other side of Switzerland, and it's on the border with France. CERN spans.
Right. Yes.
So we just use the territory. Because, we internet, and so, it's very mostly. Anyway, when I saw, I understand what it said. My wife, that I made a video in Blanket. She was part of many downstairs in Geneva, and so which this is contemporary dancing, right? So, and this guy, the choreographer, they want to skip, they want to, touch, they're not kicking. And the thing is, they think, man, because it was a tunnel, they hell with the goal that is absolutely nothing. That's what happened. I don't think they really anything than doing something different in that. But I don't know the whole story. It was completely out of place. Totally ridiculous.
Well, the translation of what the goat guy was saying as he was coming out and being revealed, as he says, "I am the king of the world." So you know, a lot of people, and this is including myself, because I do a lot of this research here to try to figure out the message they're trying to send. And the thing is like I said, the only people that were in attendance to this ritual appeared to be French and Swiss elites, or maybe even elites from around the world, but they didn't seem to question what it was they were seeing. So one, I have to look at what is their purpose behind this, and that's the whole reason why I asked you if there was any private observation, or was there any private entities that were taking an unusual interest in your activities there because of just that very thing of that ritual. You see what I'm saying?
Yeah. I mean, it's a tunnel for a railway. To do with a tunnel from Earth. It's like a tunnel. There's many tunnels in the world. And the fact that they did that thing, I'm sure that they probably had a lot of trouble from authorities, etc. for that thing, because you're not supposed to do things that, even if there were some kind of demonic sect or something who choreographed that thing, they still are pretending this to ordinary people, to the heads of states. There were heads of, like you say, of Switzerland and France. There were a lot of VIPs. And they kept them there for more than half an hour because they had to go stuff inside and then they went outside. It's totally crazy. I mean, I totally agree. These people are mad and they have absolutely nothing to do with us. So don't ask me because I think that, certain people didn't know about this. Well, when I asked my friends, they said no. Well, no. And they went to go check it out. And they laughed. The hell, the Swiss are always Swiss, Sorry for the sleeping. No wonder that
there were heads of state there. Angela Merkel was there. And I do believe a few other dignitaries from all around the world were there. And that was the first thing I asked myself. I was like, how come there isn't even a look on anybody's face like, what in the hell am I watching here? No one said that. It was like they already had a clue as to what was going on. So I'm here with you because I like to get a clue of what's going on there. But
as much as you do. I mean, I went to check it out, and I did that thing. I looked at some of the comments on it. Then I tried to find in the news what happened afterwards. They had any repercussions, and I didn't find anything. But I'm pretty sure that whoever put that show together must have had a lot of trouble. They'll be fired.
Well, you know what, sir? It was a pleasure getting to speak with you. I heard so much about you from Ian and Alex, and it definitely was a pleasure to spend some time and listening to your presentation and getting to talk with you even.
Well, I'm glad that you're welcome to interview. Also, I want to say just one thing because normally I comment from the blog. I will reply to those offline. So I will go tomorrow through the comments you send me. And I will reply to those that I have an answer for. And I would like to remind everybody if you want to be friends, request on Facebook, please say that you are in my phone because I cannot. I'm having thousands of people. I don't know who they are. These people. I don't want to have spammers and
I don't think your wife's going to be too happy with all of those bikini girl. Yeah, you're going to get in trouble over that. So I wouldn't accept those. Don't accept those.
Yeah, the Facebook has become a thing. Doesn't make us proud.
A joke? No.
Yeah.
No.
We meant the Web 3 when we.
Oh, that's what you're doing. No, I'm playing. I'm not kidding. I'm just kidding. Alex, hey, thank you very much for having me here. And Silvano, do you have anything else that you'd like to add that maybe something we didn't?
I just wanted to see what we're going to talk about. So we go with Einstein.
We're losing most of that again. But I think you're just sort of saying the next, what you've got planned for the next weeks or so, if I'm reading between the breaking up correctly. But anyway, thank you for being with us again. Thank you for all your information and for the discussion between the two of you. It's been great. We will see Professor Doom later tonight. We'll be back at 7 p.m. and we will see you, Silvano, next week, hopefully. Next Monday at 4 p.m. British Summer Time, and whatever that is, 7 p.m. down your way. Okay, we'll see you soon, guys.
Thank you, Silvano. Thank you very much for meeting with me. Bye-bye.
Bye-bye.